Okay, so the answer to this part of the question, which was at 400 K, both compounds are gases. At this temperature, which compound behaves more like an ideal gas? Remember that an ideal gas just means a gas that has no interparticulate interactions. So fewer interactions would mean that the CH4 would be more like an ideal gas. And then this question here, so pause the video, read the question, and then I'll explain the answer in just a second. All right, so when it's asking you to make a diagram of this, so you're gonna have a bunch of CCl4 molecules arranged down here, okay? A bunch of these things just copied and pasted in here all together, close together. Not super, super close, but you know. And then you will have some of them, because some is evaporated, you'll have some floating around evenly distributed. I'd do 4 or 5 evenly distributed amongst the rest of the volume of the box. You will not use this or this or this, because this is not a chemical change. CCl4 is not decomposing, it is simply evaporating. Okay? And that, my friends, is that question. Do we want to do one more review question from like 3.4? All right. Is this helpful? Yeah? Okay. I hope so, because, I mean, I want it to be. 3.4, I don't want to do stuff that's like, all these questions have to do with other topics. Let's look at this. Okay. Questions refer to 3 gases in identical rigid containers under the conditions given in the table below. All right, identical rigid containers. I feel like they don't need to tell us that it's container A, B, and C then. Whatever. Okay. So the density of the gas in grams per liter is, what? All right. So density. Does the ideal gas law have density in it? Remember what the ideal gas law is? PV equals nRT, right? Where P is pressure, V is volume, N is number of molecules, moles, R is the gas constant, and T is the temperature. So we need to do some math here. So pull out your calculators, or if you don't have your calculator. Look at that, there's a student with like kind of longish black hair sitting over there. I know it's Christian. Christian, what are you doing? Okay. So PV equals nRT. So let's look at this. Three gases in identical rigid containers under the conditions given in the table. All right. So our temperature is the same between the three. Molar masses are different. Pressure is different. In fact, we may not even need our calculators on this one. Density of the gas in grams per liter. So how are we going to do this? Grams per liter. What do you think? Come on, guys, I need you to talk with me here. There's only two of you.
Well, the same temperature, and we're using the same gas constant. I feel like it's molecules.
Okay, number of molecules definitely plays into it. Which answer can we just immediately throw out? Which two answers really? A and D for sure, right? Because methane is the lightest in grams per mole, and it has the lowest pressure, meaning that there's the fewest molecules, right? Now, where it gets interesting is that methane has twice the pressure, but almost half the molar mass as butane, right? So what can we do here to determine the density in grams per liter? If we had the same pressure, you could just simply choose the heavier one, right? Right? If it was the same pressure, you could just choose the heavier one. But because we have a different pressure, so PV, so we don't know the volume. Right? We just don't. Equals, so 4V equals, we don't know the number either. We know the gas constant, which is R, and we know the temperature, which is 27 degrees Celsius, which we would just convert into kelvins, right? Which, what is that, 27 in kelvins? It's like 286, right? Right? I don't know. Really doesn't matter because it's the same. But we know that the volume is the same between the two containers as well. So we can actually just kind of get rid of that. Okay? We can just kind of get rid of the volume. So it's 2V equals nRT versus 4V equals nRT. Right? Well, because this is double the pressure and just under less than half the mass, what does that tell us? That is what? Ethane. So the highest density is in container B. So B. Would that make sense? Sure does. Okay. If this had been 3 atmospheres, it would have been C. Right? If this was 4 No, fuel is, I don't know, I'd have to work out the math, but you could get a scenario where the density was the same between these two if the ratio between the molar mass and the atmospheric pressure was equal. Okay? Option B is correct. Since all three containers are the same temperature, the number of particles per unit volume is directly proportional to the pressure. The density of the mass per unit volume, so the density is proportional to the product of the pressure and the molar mass. This product is greatest for container B. Cool. All right, I'm gonna leave it at that. Hopefully you found these questions helpful. Bye.